Okay, welcome back, my Earth Science 119 physical geologists. So, this is our first online lecture, and we're going to be talking about some of the vocabulary involved with volcanoes today. So, just to remind you, you have your first exam on Tuesday, and this will be online via Canvas. It will be timed, so you'll need to make sure you have a stable internet connection beforehand. If you have accommodations, no worries. You just email me and I'll make sure that we work out everything for you. So, your exam will cover everything from this study guide here, except the last part, earthquakes. So, we didn't get to this yet for this exam. It will be in our exam too. So it's very important. Make sure you know that that won't be covered here, but the rest will be covered. So today our slides are week 3B. No, I misspoke. It's not week 3B. That's next week. We're still here, week 2 to 3. So last time I saw you guys, we watched that video, right? It was called Killer Volcanoes. And today we're going to go into a little bit of detail on the specifics of different types of volcanoes. Why are some volcanoes explosive and others are relatively mild? Right, so let's watch this introduction video to volcanoes.
The great enemy of writing isn't your own lack of talent, it's being interrupted.
Volcanoes have helped shape our planet. They provide life, but also can take life away. Here's our list of the top 5 volcano eruptions caught on camera. At number 5, we have Mexico's Popocatépetl volcano, which erupted in 2013. Popocatépetl erupts every few years. Nearby residents have learned to stay well clear of this volcano. Last year, Mount Shindig erupted in Japan, which covered nearby towns in ash and dust for weeks. Luckily, the volcano is situated on an island, so most of the magma flowed safely into the ocean below. These mountain climbers are certainly lucky to be alive after Mount Kushino Arabajima erupted in Japan. They quickly take cover behind rocks to shield themselves from the elements.
やばいねこれ。
下がるもっと。あそこだ、あそこ行く？
あ、行こう。まだ降りた方がいい。北小屋行こうみんなじゃあ。行こう。どうしましょう。どうしましょう。間に合わん。
Costa Rica's Turrialba volcano erupted also last year. No one was reported to have been killed, but nearby airports and facilities had to be shut down for days until the ash subsided. Perhaps the most famous of all volcanoes, Mount St. Helens erupted in 1980. 57 people died in this eruption, making it one of the most deadly volcano eruptions in modern times. Please subscribe.
Okay, so we discussed how volcanoes will always parallel convergent and divergent plate boundaries. However, some occur in the middle of the plates, and those are known as hotspots. So, what is a volcano? Right? A volcano is just very simply a section in Earth's crust where magma forces its way to the surface. Right? And ash and gases may also escape during this process. So here I have sort of a nice simplified photo and a map of the cross section of a typical volcano. So you can see at depth here in the mantle, you have the magma chamber and you have the main conduit leading to the top. But oftentimes you'll have secondary conduits. Right? And so you can get sort of these secondary cones or scoria cones that will form on the flanks of a larger volcano. The ash cloud is probably the most dangerous aspect of a volcano, right? Because it suspends and releases something called the pyroclastic flow, sort of superheated, fast-moving cloud of ash and dust that will, burn your skin off. So here we have the main vent. Here's a secondary vent here. And then we also have the lava flowing down the main flanks. So lava, right? Lava isn't the greatest threat from a volcano. It's these sort of explosive pyroclastic plumes that cause the most damage. So when we look at volcanoes, we can actually divide them into two main types. The first type are known as acid volcanoes. You may also see them called stratovolcanoes. And these are the ones that are highly explosive, right? These are the ones that have the typical conical pointy shape. And Mount St. Helens is one example. The lava associated with these types of volcanoes is very viscous. And what that means is that the lava is resistant to flow. And that's why the conical shape of these volcanoes is a result. The lava won't flow very far from the main vent, so it piles up at that vent, creating the triangular shape. And you get acid volcanoes at places where you have convergent plate boundaries, where ocean crust is subducted underneath continental crust. So the Cascade Range, Mount St. Helens, those are examples. The Andes, South America, that's another example. The second type of volcanoes are known as basaltic volcanoes. You may also see them called shield volcanoes. And these are less explosive, right? These are the ones that aren't as dangerous. So for example, Hawaii is probably the most famous basaltic volcano. And you may know that Hawaii is not explosive, right? People have their homes right on the flanks of this volcano. And these types of volcanoes can be found at both hotspots and also divergent plate boundaries, also known as rift zones or the ocean ridge. And the reason that these volcanoes are not explosive is because of the magma component. The chemicals present in the magma make the lava less viscous or more willing to flow, right? So you can sort of think of these two different types of volcanoes in terms of their lava Think of the lava like syrup, right? Cold syrup is very viscous and thick. It's resistant to flow. Whereas warm syrup is more runny, right? So that's like the Hawaiian lava, basaltic volcanoes. The lava is very runny, so it moves away from the volcano. It spreads out in all directions, giving the volcano a more shield-like shape, right? It's not a pointy shape. So highly explosive versus less explosive has to do with what's being melted. Acid volcanoes, you're melting continental crust, and the minerals and chemicals that make up the continental crust are more acidic, so they're explosive. Whereas with basaltic or shield volcanoes, right, you're melting ocean crust, which is different, very different than continental crust, and less acidic, and therefore not explosive. Okay, so now let's go into a little more detail looking at acid volcanoes. Also known as stratovolcanoes or composite volcanoes, they're formed of layers of both lava and ash. Like I said before, the lava is viscous, resistant to flow, which means it builds up close to the vent, resulting in the distinct cone shape. The lava itself is high in silica and low in iron and magnesium. These types of volcanoes are found at ocean continental plate boundaries, and the melting is a result of that plate subduction. You get explosive eruptions when you have the presence of water vapor and gases. This is oftentimes the first thing that will occur during a volcanic eruption. Here we have some famous stratovolcanoes. Mount Fuji in Japan is, of course, one of the most beautiful. Another famous stratovolcano is Vesuvius in Italy. So some of you may have heard the story of Pompeii. These ancient Italians built their civilization on the flanks of Mount Vesuvius. And when Vesuvius erupted, the associated pyroclastic flow encased the people of Pompeii. And you can go, someday, if you can ever go back to Italy, you can go and you can actually see their bodies preserved and encased in that volcanic ash. So location of stratovolcanoes is at convergent plate boundaries, where you have ocean crust being pushed down underneath continental crust. So this picture here shows the Cascade Range that extends from Northern California all the way up to Vancouver, British Columbia. And here's some of the pictures of these stratovolcanoes. Okay, so the second type of volcanoes are the basaltic volcanoes, also known as shield volcanoes because they have a shield shape. And these volcanoes are formed from widespread layers of lava that are low in silica and high in iron and magnesium, which is the opposite to the constituents of strato or acid volcanoes. The lava is low in viscosity, right? So think hot syrup. And so it travels very far away from the main vent. This is why you get the creation of such large, geographically widespread islands. It's because of the lava's ability to travel, basically. So you can find them at oceanic hotspots, and the eruptions are not explosive. So Hawaii is one of the most famous basic or shield volcanoes. Oh, well, not available. Okay. Okay, so here I have a picture of the largest shield volcano in the solar system. So this volcano is called Olympus Mons, and it's located on Mars. And this shield volcano is 3 times taller than Mount Everest. It's pretty incredible. And when we think about the reasons why, right, why is this volcano on Mars so much bigger than anything we could find on Earth? Well, Mars isn't thought to have plate tectonics. right? So the surface isn't in motion. And what this means is if you had a hot spot on Mars, right, there's no plate to move over it. So instead of getting a distribution or a chain of volcanic islands that, grow and age as you move away from the hotspot, instead, all that lava piles up in one spot. So because of that, you get a much larger topographic feature. Calderas are collapsed volcanoes. So this is where you could get a magma chamber has emptied out, and as a result, the ground collapsed, right? It sinks down, and oftentimes it can become a lake. And one of those examples here, a really beautiful, famous example, is Crater Lake in Oregon. So this caldera used to be a stratovolcano, right? So you can follow the orientation of the bedding upward. But at some point in the past, it blew its top, right? It blew its top, and so the ground sunk below the empty magma chamber. And here, this little feature is called Wizard Island. This was a little baby vent. That's the last active volcanism in Crater Lake. So occasionally, a caldera can sometimes transform into something called a supervolcano. Right? So supervolcanoes form where you have the collapse of a pre-existing volcanic structure. Right? So you create more surface area for that eruption. Some other examples of calderas come from Santorini. So this volcano actually destroyed the Minoan civilization due to its tsunamis circa 1600 BC, and actually may have given rise to the Atlantis myth. So pretty cool. And I actually had a student last semester, she presented a research project on this. Right? She wanted to find the timing between this eruption and some of the archaeological records. For classifying volcanoes, right, we use something called the Volcanic Explosivity Index. Right? It's a relative measure of the explosiveness of volcanic eruptions. So similar to how we rate earthquakes with magnitude, right? Magnitude 1 to 10. This is similar in that the scale is logarithmic, right? It's not linear. That means each interval on the scale represents a 10-fold increase in the observed ejecta criteria. So it runs from 0 to 8, right? 8 is the maximum you can get on the index. And so this is dependent on how much volcanic material is thrown out, right? The volume of that. To what height does the ash cloud reach? And how long does the eruption last? Over here, you can see a comparison of some of the most famous volcanic eruptions. So Mono Inyo craters, this happened in the past 5,000 years. Some of you may have been to Mono Lake. It's a couple hours from Los Angeles. But you can see these really thick, rosy colored volcanic deposits from the recent eruption. Mount St. Helens, which was in 1980, was roughly a 4.5 here size on the Volcanic Explosivity Index. Pinatubo in 1981, about a 5.5. And then Tambora, the largest volcanic eruption observed in modern history. That was about a 6.5 in 1815. So that's greater than 100 kilometers cubed. What's not displayed is the Yellowstone caldera, which last erupted 600,000 years ago. Right? This eruption was, if we compare it to Tambora, probably a 7.5 to an 8. And it's not pictured here because it's too large. Right? It wouldn't fit on this whole diagram. That's how big it was. Okay, so following from that, when we look at the Yellowstone caldera, right, we can ask, can hotspot volcanoes occur on the continents? We talked a lot about them in the oceans, right? Hawaii being the main example. But can they occur on the continents? And the answer is yes. Continental hotspots are much more catastrophic than their oceanic counterparts because you are melting continental crust. Remember, high in silica, low in magnesium and iron, which means that the explosions will be devastating. And a lot of scientists believe that hotspot eruptions on land have actually caused some of the mass extinctions throughout Earth's history. And this is achieved by, remember, when you get a large eruption, enough ash can go up into the atmosphere and block out the sunlight, right, for years. And that will completely alter the climate system. It will keep life from being able to photosynthesize, and it will cause mass ecological collapse. And Yellowstone is an example of a continental hotspot, right? It's pretty well studied, and it's very well monitored by USGS for earthquakes and magma movement. So although it's unlikely, right, the Yellowstone supervolcano will erupt in our lifetimes, it is said to be, overdue, in the sense that we could expect one in the next, it could be tomorrow, it could be in 1,000 years. Here we have shown the progression of the Yellowstone hotspot. So the most recent eruption is shown by this yellow blob here. Okay? And then you can see each of the prior eruptions. So they get older and older. The numbers here indicate millions of years before the present. So this would be 16.1 million years ago, 10 to 7 million years ago. So the last one was around 0.6 to 2.1 million years ago. So you can see that there is a lot of leeway, right? So if people try and tell you we're overdue, tell them that that's, it's kind of ambiguous, to be honest. But you notice that there is this chain, right? So similar to Hawaii, right? The Hawaiian Islands also make a chain like this, right? So from that, we can infer which direction the North American plate is moving, right? So we know the hotspot is situated somewhere around here, right? And the North American plate is moving along this direction, away from the hotspot. So how do we create a supervolcano, right? So stage one is you have the magma source, right? This magma pipe that will rise up, the mantle plume, right? The stable mantle plume will rise up and melt the base of the lower crust. And as that occurs, you will get a bulge, right? And this actually occurred at Yellowstone a couple years ago. The land started to bulge outward and stretch, and all the scientists were freaking out. They thought there was going to be an eruption. But you had some magma movement, not related to an explosive eruption. And during this time, as the crust begins to heat up, it will fracture, right? Cracks will appear on the surface. Gas and ash will erupt from the magma chamber through these cracks. And eventually, the magma chamber will collapse and a depression is formed. This depression is called the caldera. But notice here, the magma chamber is not depleted. Right, so some of the worry here is that the caldera provides more surface area for this explosive eruption. So not all calderas will become supervolcanoes, but all supervolcanoes start off as calderas. Here we have a map of all the known supervolcanoes in the world. So we can see we've actually got quite a few over here on the West Coast. We're so lucky, right? But they're not that common. All right, so that's the end of your lecture for today. I know it was a little short because we were supposed to cover this last week. And if you guys have any questions at all, I will be on Canvas. You can send me a message to the app for the quickest response.